So I recorded a video recently that talked about the rendering performance of different Rust WebAssembly front-end frameworks. In other words, you write an application in Rust, you compile it to WebAssembly. How quickly can it update the DOM, what you actually see in the browser in front of you, relative to a kind of vanilla JavaScript hand-tuned implementation that measures how fast the browser can render things. JS Framework Benchmark is kind of the greatest benchmark for doing these things because it tests a variety of different operations you might want to do. After I recorded that video, one of the maintainers of U, which is by far the largest, the most popular, the most mature Rust WebAssembly front-end framework, reached out and said they actually had a known regression that had affected that benchmark that they had fixed in Git in their repository, but they hadn't re-released yet and hadn't updated the benchmark. So sure enough, I checked it out. I looked, they had really improved the performance relative to what was in that benchmark. But I had also in my work looked at some other optimizations that I hadn't seen in U, and I wondered how much faster we could make U in this benchmark. And so I thought I would show you a few of the things I tried and show you the results. So if you don't know the benchmark that I'm talking about, it's this JS Framework benchmark. It's basically table operations. So you do things like create 1,000 rows, swap the second and the 999th row. You can delete rows. You can sort of change the color when you select a row. You can update every 10th row, adding these exclamation points. You do things like creating 10,000 rows, which takes a long time in any framework. So how did U stack up compared to other frameworks? So this is the results that I ran, not the official results, but the ones using U's master branch. And I just have, for comparison, React is the column on the right, and Preact, which is another virtual DOM framework, works a lot like React or U does. Also in JavaScript, just like React. Preact is on the left here, right? So overall score, React has a 1.83, which means it's roughly 83% slower on average than that hand-tuned vanilla JavaScript fastest possible implementation. Preact was about 40% slower, and U, this is U's master branch, was about 52% slower, which isn't bad. U is a lot faster than React in terms of rendering speed in this benchmark. But I did want to try out some optimizations, and I was just wondering how close can we get it to something like Preact? I think a great goal for Rust WebAssembly front-end frameworks would be for similar frameworks to have similar performance to their JavaScript equivalents, which with the current way that WebAssembly works in the browser, the JavaScript version will probably always be a few ticks faster than the Rust WebAssembly version. So for example, if U could be the same speed as Preact, if Sycamore can say, yeah, we're at least as fast as Svelte, if Leptos can say, we're almost as fast as Solid, Dioxys is almost as fast as something like BlockDOM or MillionJS 2.0, that's a pretty good story. So I took 4 different levels of optimization, I applied them to U, and I wanted to see how quick we could get. So a pretty good amount faster. If you look at the top line numbers here, that's from 1.52 for the current master branch of U down to a 1.43 once I had applied all my optimizations. In other words, that's 20% of the difference between what U is currently doing and the fastest that the browser could possibly go. But I don't know anything about the virtual DOM. I didn't touch any of the virtual DOM code. I didn't touch anything that compared these lists, anything that compared those text nodes. What I do know is a little bit about how WebAssembly and the browser works. And so what I did was try to find optimizations that would speed up these element creation costs, which are a lot of what you do in applications. You create a lot of elements to display on the screen. So if we take away all the benchmarks that are virtual DOM reconciliation things, like partial update, adding those exclamation points, select row, figuring out which row was selected and changing the color, remove and clear rows, list reconciliation, and swap rows, which is detecting that you've swapped the second and the 999th rows. And we just have the ones that are element creation. In other words, just the places where we're shipping things from Rust WebAssembly code over to the DOM itself. You can see the effect is even more drastic. So current U was 1.75, 75% slower than the fastest possible implementation. And with these optimizations, we got it down to 0.53. In other words, that's about a third of the distance to the fastest possible browser implementation. So I thought that was pretty good. So what did I actually do here? You'll see there are 4 different versions, there are 5 versions of U. One is the baseline, and then 4 optimizations. Intern tags, intern attribute keys, intern attribute values, and clone nodes. Okay, so what does all this mean? Let's take a look first at what interning is. So if we want to figure out how to make use element creation faster, which is most of what I was looking at, it makes perfect sense to start in a function called createElement, right? This is the place where, after all of its virtual DOM work to figure out what manipulations need to happen in the DOM, U actually goes and creates those elements. Because U, like any virtual DOM framework, works by constructing a virtual DOM tree. In other words, a data structure that represents the structure of your HTML or of your DOM nodes, but without actually rendering them. And then it compares it to the last version of that. It gets these diffs and patches, then it applies them. And sometimes that's something really precise, like update this one text node. But sometimes it's, hey, create 1,000 rows, right? So I thought there was a lot of benefit to be had in this createElement function, which is where the rubber hits the road. If it says there was no element here before and now we need an element, we call createElement. So this first optimization, intern tags, you'll notice that was about a 5% increase relative to the raw version here. And get ready. So there's a document.createElement call here, right? This is the same as in JavaScript, document.createElement. And do you know what the optimization was? I said it was interning tags, right? So we call intern tag. Okay, maybe we should import that. So what is intern tag? Let me get my video out of the way. Okay. Oops. Intern. Interns Rust strings, so it's much faster to send them to JavaScript. All right, so this comes, you can see, from WASM bindgen, which is the crate that's used to sort of generate the glue between Rust WebAssembly and JavaScript. It's a WASM binding generator, right? So if you've seen any of my other videos, you may know that Rust uses UTF-8 strings, and JavaScript and the browser use UTF strings for a mixture of technology choices and historical reasons. So to ship a string from Rust WebAssembly over into JavaScript means you both need to byte-wise copy it so that you have a WebAssembly string on one side and a JavaScript string on the other, because WASM and JavaScript don't share memory. And then you need to re-encode it from UTF-8 into UTF-16, and this is quite a slow process. For things like element names, this is really slow, because if you think about it, looking at the benchmark, right? When I create 10,000 rows, I'm creating 10,000 elements, and each row is a TR, and then TD, 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 TD. This means that for each row, I have to copy the 2 bytes TD, and then re-encode that from UTF-8 to UTF-16 string, and I have to do that 4 times per row. So when I create 1,000 rows, I have to do that 4,000 times. When I create 10,000 rows, I have to do that 40,000 times. This is relatively expensive work. So what string interning does is it caches that work. So let's look at the actual implementation of intern here. It calls this intern string function inside WASM bindgen, which is fairly straightforward. You'll see it creates a thread local cache, which is just a ref cell around a hash map. If you're a Rust user, this should be fairly familiar language to you, but it's basically just a way of saying, hey, here's this hash map that I might mutate. And it's a hash map where the keys are strings, and the values are something called a JS value. Now, a JS value is basically a JavaScript object in a heap, an index to that object. So WASM bindgen keeps a sort of heap of JavaScript objects over on the JavaScript side, and then it sends back these JS values, which point into that heap. So in other words, calling intern here takes a mutable reference to the cache, checks if it contains that key, and if it doesn't, well, it creates a JS value from that string. So it copies TD, converts it to UTF-16, makes it, puts it in that heap, and then sends that index for it back over into WebAssembly, storing it in the hash map first. Then when you essentially unintern a string, well, it's right here, that's removing it. If you get the string, you basically look it up in the hash map, You see what the index is, and you send it, which means that now if we call intern string, if it doesn't exist yet, we store it in the hash map. If it does exist yet, we don't create another JS value. We just return the JS value that's already stored, which means when we create TD 4,000 times, we only have to copy and transcode the string TD once. The other times we're just looking it up in the hash map, which is significantly cheaper. So again, like I said, that change was responsible for a pretty good improvement in terms of element creation speeds. And that's just applying it to tag names, to your table, tr, td, and so on. What if we applied it to a few more things? So if you look back in the benchmark, we do have lots of other repeated strings we're shipping all the time. So if you just look in this snippet, right, you can see class is one of them. Div class equals container, class equals jumbotron. But especially when you create the rows, class equals call medium 1, class equals call medium 4, class equals label, class equals call medium 1, and so on. We keep shipping this string class over and over and over. So what if we intern the attribute keys too? In other words, the attribute names like class, like ID, that are repeated over and over again. So to do this again is really simple. We went into attributes where they have a set attribute function. So if the virtual DOM diffs it and sees that you need to change an attribute, or if you're creating an element, it calls l.setAttribute, which is exactly the same as the JavaScript function that does that. And again, we're going to use WASM bindgen interning, and we can just intern those attribute names like class, like ID. I did the same thing, by the way, for event listener names like click, things that tend to be repeated a lot. We don't need to copy that 100 times and send it over into JavaScript. So what was the effect of that in the benchmark? Well, that got us another 0.05. So we've gone from 1.74 down to about 1.64, which is pretty good. Again, that's like a seventh of the distance between you and native rendering in the browser, right? The fastest the browser can go, with again, 2 function calls inserted, right? And I should add, do I have cargo.toml in here? No. What you need to do to actually use this is to go into WASM bindgen and enable the enable interning feature. Now the U team made what's probably the wise decision that they don't want to enable this by default. So if you as a user want to enable this, you can actually add a WASM bindgen dependency to your own application and enable the enable interning feature. The intern function without this feature enabled is just a no-op. It doesn't do anything. So in other words, there's no cost to this for somebody who doesn't want to use it, but if you do want to use it, it's all set up. But what is the cost if you do want to use it, by the way? That's important to talk about, because the reality is with any of these performance things, there are trade-offs. So obviously there's a nice performance boost. You'll notice though, in this total kilobyte weight, right, this is the amount of WebAssembly, JavaScript, CSS, everything you're downloading, there's about a 5 kilobyte increase. So the total U package for this benchmark was 342 kilobytes. With interning, it's 347. And that's not great, right? 5 kilobytes is 5 kilobytes, but this is 5 kilobytes un-gzipped. It's in opt level equals 3, meaning it's the compiler is optimizing for speed, not optimizing for binary size. And of course, the cost of downloading and compiling WebAssembly is much less than the cost of downloading and parsing and executing JavaScript, because WebAssembly is a binary format. You'll also notice that it's a static 5 kilobytes. So my 3 interning examples, it added 5 kilobytes relative to not interning at all. But when we intern tags and then we intern attribute keys, it actually doesn't add anything to the binary to also intern attribute keys. Of course, there's another level we could go, and in this benchmark, it actually really does make a difference. We actually squeezed another 0.07 out of this one, which was interning attribute values. So far we've interned the tag names like TD, the attribute names like class, but not the values here. But you notice there are some repeated values like call medium 1, call medium 4, label, call medium 1, call medium 6. If you do this 1,000 times, you're saving yourself. Each of these is 8 bytes long. So 1,000 rows, 8 bytes times 4 of those, 32. That's, call it 35,000 kilobytes of text to be copied and re-encoded when you create 1,000 rows. So that's kind of a lot. So I did just try out you know, going back into my, oops, goodness. Going back into the attributes here and interning values too. Now there is a real trade-off to this, right? Because in most non-benchmark applications, most of your attribute values are actually not repeated a lot of times. So if you think of something in a kind of Tailwind app, right, where you've got a class name that's 12 classes long, it might be, you know, 40, 50 bytes of text or whatever it is, probably even more than that, 100 bytes, but it's unique. Well, you remember with interning, right, we always pay the cost of this intern string call. So we're always going to hash it and store it in the cache, even if we only use it once. What that means is that if you have strings like tag names, like attribute names that are used often, they pay for themselves pretty quickly. But in a real non-benchmark application, you usually have attribute values that actually aren't reused that often. And so you're actually paying a cost here that you're not reaping any benefit for. So when the U team decided to merge the PR that I made with these optimizations, they actually said, let's not do attribute value interning, which I think outside the context of a benchmark makes a lot of sense. And of course, you can always opt into interning in your own app. So in other words, I don't have the U implementation right here. I probably should, but when you do something like, you know, well, you can say intern some class here, right? There's nothing stopping you from manually interning values that you want to. So those were the first three levels of interning tag names, interning attribute keys or names, and interning attribute values. And you know, taken together, those accounted for between 1.74 to 1.57. 0.17 out of 74, or whatever the math is on that, a pretty good improvement. Again, maybe a 20% improvement in speed relative to the fastest that the browser could render. But there is another thing that got us a little bit faster, and this one is a little more counterintuitive, and it's where you start running into some trade-offs with the simplicity or the legibility of code. So I want to talk about this node cloning approach for a minute. So if we go back into this create element call, I don't know if you know this, but there are actually two ways to really easily create an element in JavaScript in the browser in the DOM. One of them is document.createElement tag name, right? The other one is to already have an element and then to do clone node. Clone node takes an existing DOM node and clones it. It doesn't just clone a reference to it, so it's referring to the same thing, but it actually clones that node. It strips away any event listeners, but it takes the tag name, the attributes. If you do true for deepness, it takes its children along with it too. And strangely enough, in every browser I've tested, clone node is actually faster than create element at creating elements. So we're actually going to do something that's maybe a little counterintuitive and not use create element to create our elements, but actually use node cloning. And you can think of this as being a little bit like interning elements, where we had interned strings before, right? Because what we want to do is to create one element and then just clone that element for that particular tag type, rather than creating new elements every time. So in this case, we're going to create another thread local, just like the interning had. And let's call this cached elements. And we're going to wrap a ref cell around it. And the key will be a string, which will be the HTML tag name. And we'll have an element, which will be the value. And we're just going to use defaults here. We could do something like having a particular capacity that we start with, but I'm not doing that in this example. And looks like we need to import ref cell. Good. All right, and then what do we want to do? We want to say look it up in the cache. So let's say let cached equals cache.get tag, right? The tag name that we're looking for. And if we do have an element, we want to clone that element. And for now, I'll just unwrap this instead of giving a nice error message. And then we're going to convert this into an element with this WASM bindgen JS cast, which converts some type, right, into an element. I guess we maybe don't actually need that. Oh, it's because, clone node, I think, returns a node, not an element. So we get an HTML or a DOM node type, and we want to convert it into an element. And then if we need to check to see, if it already existed in the cache. So did we get a value out? So what we want to return is cached. And then we'll call unwrap or else. So if cached was none, in other words, if it didn't find anything in the existing cache, what do we want to do? We want to create an element that we're going to cache. So let's actually just go up here, grab this, create the element, right? And let's call it to be cached. And then we want to insert it into the cache. So have I actually taken no, I haven't taken a reference. Oh, and I've completely done this wrong as far as how thread locals work, which is we need to do cached elements.with cache. And that will get us a reference to our cache. And then we'll take a mutable reference with let cache equals cache.borrowMute. And let's make this mutable. Okay. So now, and that is fixing up all of our type inference too. So in other words, the way thread locals work is there's this with function that gives you access to the value inside the thread local. Now we've got the ref cell, we take a mutable borrow, we look up to see if there's already a cached element of this tag name. If there is, we clone it, we return it, and then we return that value. And if it doesn't exist, we create the thing that's going to be cached. We insert it into the cache, right? So this is what we're missing. So we want tag.toString and to be cached dot clone node dot unwrap dot unchecked into. So the same exact thing we just did, and then just return to be cached. So this is a little more difficult to understand what's going on, right? You need to understand that we're caching the elements here, that we're using clone node instead of create element, and it adds a little more additional complexity. So again, there's a trade-off. If you look at the binary sizes again, right? The current U version with no interning, without these optimizations, was 342. We added 5 kilobytes with interning. We add another 5 kilobytes to 352 with this node cloning. However, that buys us a pretty significant speed up so that the total for those 10 kilobytes of WebAssembly is about a third of the distance between you and the browser rendering as fast as it can. To me, that's worth it. Of course, if you want to turn off the interning, you end up somewhere between these 2 points, and you save 5 of those kilobytes if you're in some really binary size critical situation. And by the way, I should go back to this. Now I'm actually going to remove the interning from the tag name, because if you think about it, each of these tag names is now only going to be used once because the element itself will be cached. So when I say used, I mean create element will be called create element div a whole bunch of times or something, but we'll look up div in this hash map on the Rust side every time after that first time. So we actually don't want to intern the string now, because it will end up in that situation of the attribute values where there's no real value. We're caching that string once, but we're never looking it back up again, because instead we're looking it up on the Rust side here. So I was pretty happy with these improvements. I made a PR to you. They just actually merged the PR today, which I think is pretty great. And I hope that this was helpful for you in terms of understanding a little bit of some of these optimizations, but also some of the trade-offs involved in any optimization decisions like this. And I hope that you're enjoying yourself and creating great web applications with Rust. Take care.